Okay, so we will move towards exploring whatever we were exploring last time, and then we will move something different today. Okay, so I think last time we did design an algorithm for vertex cover, right, with running time roughly 1.3803 to the power k n to the power big of 1, right. And I said that we do have some ideas by which we should be able to go much below 1.38, and I asked you all to explore. How many of you had a time and opportunity to explore? Yeah, a couple of you emailed me. It's not that I had a time to read everything in detail, but I did read something. Vishal, did you have opportunity to think about it? Correct. I see. Okay, that's a good point. Anybody else have the opportunity to think? Okay, I'll do it, don't worry. But if you want to get the best out of the course, or if you want to get best out in research, it's in your interest that you think these things. Of course, I can give you assignments and but like I believe that at some stage in life and career, if this is the path which you have chosen, then there has to have some, what do you call, some amount of responsibility on you too. Otherwise, it's like, otherwise there is absolutely no point of lectures, you know. These are like, you know, reading some philosophy books. So it is important that you spend time thinking on problems. At the end of the day, or at the heart of the research is about problem solving, right. Knowledge is just a marker that provides us source of inspiration, but at the end of the day we have to take that knowledge and able to produce new knowledge, right. So you need to practice to come up with new knowledge, right. Okay, anyway, so let's write down this algorithm for, say I wanted to algorithm for coming up with a vertex cover of degree at most 3, a good algorithm for vertex cover, which I will use as a subroutine in a algorithm of higher degree, or when I try to come up with an algorithm of general graphs. Okay, so C equal to phi, okay, and I can say while cardinality of C is less than equal to k and j is not empty, and what will be the property of VC degree 3 graph, that so the invariant which I will always maintain that this graph has a vertex of degree at most 2. Okay, so the invariant is, what is an invariant? Invariant is, okay, input always has a vertex of degree at most 2. Okay, so this is an invariant which this graph has. Okay. Now what I will do, pick a degree 2 vertex in G, okay, and what did I tell you to do? Say 3.1, you fold V, okay. So you made V, maybe best is to, okay, folded V meaning what? If I had a degree 2 vertex, if you recall correctly, right, you deleted V and made a vertex which was adjacent to these guys, and this is what I meant by fold V. Okay, what else we did? What else should we do? Look, this graph has to have a degree at most 3. So if I fold V, what could happen? The vertex of this degree, the degree of this vertex could increase. So immediately I have to check that if this happens, I should immediately try to recursively reduce my graph into the recursive or the invariant that I wanted to maintain. So what I should check at this point of time, okay, say if the new vertex V0 has degree greater or equal to 3, okay, then branch on V. Right? This is what this is my algorithm, right? So what I do, this is very fairly simple algorithm. It's an algorithm for degree at most, graph of degree at most 3, okay? And with an invariant, there is always exists a vertex of degree at most 2 in this graph, and I would like to maintain this invariant from the beginning itself. So now notice, so because I know there exists a vertex of degree at most 2, I can fold this vertex. If I fold this vertex, it's possible that maybe this vertex now merge and it has become degree 4 or so, right? In fact, it could become degree 4, it could become degree 3. So I just check whether this vertex has degree 3 or not. If this vertex has still degree at most 2, I do not care about this because this is the kind of graph which we have and we are very happy, okay? But notice what happens if just 2.2 applies. What happens just 2.2 applies? It's just a reduction rule, right? So now it is basically T of k is less than equal to T of k minus 1, right? So this is why I say that what is reduction rule? It's a branching rule with just one child, right? That's it. But now what could happen? But if 2.3 does, now suppose 2.2 also applies and 2.3 also applies. What is the meaning of that 2.2 applies as well as 2.3 applies? If 2.2 and 2, it means what happened is that I folded V, right? Here I made some vertex V0, right? Now when I folded here, k dropped to k minus 1. Now here the moment I see V0 and it has degree 3, I am telling you to branch on the vertex V0. So now what happens? So now k becomes k minus 1, and now you are branching at this stage in one branch where you include V in the solution, right? And in the other branch you take away these set of vertices. So how much do I drop? 3. So overall drop, when I look at here in this little subtree, how much it is? 1 plus 1, 2, 1 plus 3 is 4, right? So at this stage, so now I am saying, look, let me, so I started with a tree. I said, okay, like I know how many, so here there is only one child. So I said, okay, fine, compute the number of leaves in the tree with at most k minus 2 when we are looking for a vertex cover of size at most k minus 2, and in the other tree we are going to look at the vertex cover of size at most k minus 4. So the recurrence here is given by how much? And this should solve something. Yeah, but then that's better for me, no? It cannot be 4 or 5. I think it can at most be 4. Because they are also neighbor to V, right? So when you delete them, okay, 2 to 4. Yeah, right? But at most, but I say, look, at least they will be, so the only time when I'm branching, when their vertex is of at least 3, okay. Now you tell me why there is a vertex of degree at most 2 here, why is a vertex of degree at most 2 here?
Because the neighbors of the new created vertex V0 can have degree.
So V0 is the only vertex with degree 4, every other vertex has degree at most 3. So when I delete V0, right, I still create vertex of degree at most 2, right? When I look at all the neighbors of those guys, I will still create a V0 itself is of that kind of vertex, degree at most 2, right? So in both branch, I have maintained my invariant that there exists a vertex of degree at most 2. I have never said vertex of degree at most 1 or so, no, or equal to, no. I am saying the invariant is there exists a vertex of degree at most 2. So if we could come up with an algorithm that somehow guarantees that in the beginning I have a vertex of degree at most 2, then I can maintain that as an invariant throughout this algorithm. Now all of you have mentioned to me is that, hey, why is this true even? So in the beginning I have a graph G. If G itself has a vertex of degree at most 2, don't worry, because once I feed this graph to this algorithm, it will always maintain this property that there exists a vertex. So the only problem it could have that in the beginning graph does not have any vertex of degree 2, but G is 3 regular. Okay. Then what did I told you? I told you that in this case we can do something very simple, is that look at a graph G and pick up some edge UV. Pick up some edge UV and make the following transformation. So what's the transformation we are going to make? I said, okay, you make UV, subdivide this as twice. Okay, so x1 and x2. Okay, now we can show that G has a vertex cover of size at most k if and only if, say, call this graph G prime, has a vertex cover of size at most k plus 1. Okay. Now you look at any vertex cover of size at most k, you delete it. Okay, you delete it. What the only thing which can be left, right? The only thing which could be left after you delete this, right? So because edge UV is there in this graph, either U or V must be part of your solution, right? If at least one of you, so if you take this, only thing which you have to take care is possibly this edge and this edge, then you can pick x2. If V is in the solution, then probably you only have to take care of these two, then, or if both are there, then only you have, like, all I am saying, in every case you can either pick x1 or x2 appropriately and get a vertex cover of size k plus. Now if you look at a vertex cover of size at most k plus 1 here, because x1 x2 is an edge, you have to at least pick x1 or x2, right, and k size solution here, right. Now if you go here, right, if you pick just x1, right, it means what? All other, look, if you did not pick, if you have just picked x1, what does it mean? That it just means that, and suppose you did not pick any u or v, okay, then you know that all the neighbors of u are picked in the solution, all the neighbors of v in the picked in the solution. Only edge which needs to be taken care here is the edge uv, but you have an extra, like, and how much have you used up here? Look, you are looking for a k size solution. So suppose,
In that case, V must be there.
correct, okay, okay. So suppose I have a k size solution here. Now notice, if, look, if neither u or v is there, then both x1 and x2 must be there. Okay, if both x1 and x2 is there, then that's very easy, because how much did you pick from here? K minus 2, right? And this k minus 2 set covers every edge here except the edge uv, right? And for
Probably K minus 1.
Because we have taken x1 and
no, he's right, k minus 1, because we have k plus 1, no? Okay, so k minus 1, but now I have an extra budget to pick one of u and v, so you can take care. So you can similarly argue, this is like, this is a very trivial reduction which we, so all I am trying to tell you is that now because of this, what can I feed this graph? I can feed this graph this g prime comma k plus 1. So it's like my algorithm running time will be something to the power. So if you do this recurrence properly, this is like 1.272 to the power k that it solves to. So it is like 1.27 to the power k plus 1, and that's big. Okay, so we can solve VC degree 3 in time. This algorithm will solve you Okay.
Yeah, I have a question.
Yes.
If without doing this thing, if we first do this branching on a degree 3 vertex,
Yeah.
and then after
Yeah, you can do that. But it's for me just cleaner, right? Because I don't have to think like separately that okay, now first let's branch on this and then we will maintain this invariant, which is also perfectly fine.
Maybe supposing that if we also count the lower degree, then we can improve this.
If we can count,
In our whole process, we are only commenting on at most degree.
I didn't get your points.
This thing we are following, we always say that at most degree is this much.
Huh.
We take in consideration and then we proceed. For this recurrence, I have this feeling like if we comment on lower degree, that no vertex has degree lower than this.
Hmm.
That also might be having in terms of
Yeah, but the lower degree vertex could also exist, no? So we need to handle them somehow, no?
because if you just see the recurrence relation, you can see like if you manipulate it, like before it was k minus 1 and something k minus higher number. Now you come up with k minus 2 and k minus 4 and our this things improves.
Correct.
So I have this idea like if we comment on lowest degree, that lowest degree cannot be lower than this much, then also
Yeah.
singular.
Yeah, but how to make sure that you increase the degree of a graph, right? It means I need to branch or something, right, in a way that I am able to handle low degree vertices, right? So all we are able to do at this point of time is to handle degree 1 vertex and degree 2 vertex. So I can only ensure that the minimum degree of my graph is at least 3, right? By not doing anything, by some simple operations, I can make sure my graph has minimum degree at least 3, right? But I do not know the reduction rules or which can make graph minimum degree 4, say. There are rules which can make graph minimum degree 3 to 4, like slightly, but there are many rules which does not apply. So if there are no known reduction rules which given a graph G and a number K could come with a graph G prime and some K prime where G prime has minimum degree at least 4, for example. So this is a nice combinatorial question if you can come up with, but it's just that I am not aware. Okay, so this is our algorithm for VC degree 3. Now I want to have such an algorithm for VC degree 4, okay, and I want an easy algorithm, not as complicated as some people have sent me.
Here the parameter increases.
Yes,
So our T of k will be less than or equal to T of
K plus 1, so that is what 2.7 to the power K plus 1.
Okay.
So you take out 1.272 here, that's still a constant, right?
Yeah.
Yeah, of course. Okay. Okay. So I want to do now VC degree 4. Okay. So I want to come with a good algorithm for VC degree 4. Why? Because if I have a good algorithm for VC degree 4, then for a general algorithm, I will branch on vertices of degree at least 5. That will give me good branching algorithm or good recursive algorithm. And the moment graph has becomes maximum degree at most 4, I will fall back on the algorithm, this particular algorithm. So like I can call this algorithm as a subroutine and get a good algorithm, right? So for 4, I could use an algorithm for 3, right? So similarly for 5 or more, I could use this as a subroutine. So this is how, look, people iteratively make an algorithm, right? So what is an iteratively? Okay, let's try to understand what can we do good about 3. Then iteratively, what can I do about good 4? Okay, and if you can do 5 also very good, then 6 onwards you will start getting closer to the what is known best. But I will not go that much. It's like it's painful. After some point of time, it's painful. Okay, I'm just doing this to show you. Generally, I don't even teach this much. Okay, so let me see. Okay, so what I want to teach you now, so let me see the algorithm which I wrote. Okay, so let's try to ensure what can I do about this. Okay, so what is going to be, so okay, again, what's my invariant? Let's try to have an invariant. So what is an invariant? Invariant is, okay, G always has a vertex of degree at most 3. Okay, so that's an invariant I'm going to maintain. And how can I ensure that? I start with, if I started with 4 regular graph, then I will do the same operation. In fact, there exists a vertex of degree at most 2. So in particular, there exists a vertex of degree at most 3, right? So I can apply this reduction rule and ensure that in the beginning we do have this property, and after that it is the job of my recursive subroutines to take care that such a vertex always exists. Is that fine? Okay, so exactly the way we did for 3, we can do it for 4. So just know this subroutine. Okay, so now I'm going to run this. This is my workspace. Okay, so now so what could be my first case? Like, I think again we can do something. Okay, so C equal to phi. Okay, second, while mod C is less than equal to key and G is not empty. Okay, now what I do, 2.1, if delta of G is less than equal to 3, then what should I do? I can call this algorithm, right? So this is exactly why I made this algorithm. Okay, I want to see if, okay, so now what we know here, plus there exists a vertex of degree most 3. What does that mean? What does that mean? Can I assume after this, okay, here's my lemma or small observation. If maximum degree of the graph is 4 and there exists a vertex of degree at most 3, okay, if there exists a vertex of degree at most 3, okay, and or say of equal to 3 and a vertex of degree 4, then there exists a vertex U whose, okay, so let me, okay, then there exists a vertex V who has a neighbor Z whose degree is 4. Yes, Pallavi. Yes, Pallavi.
So in the degree 4 case, our invariant is that graph is the vertex of degree at most 3.
There exists a vertex of degree at most 3. Correct.
Right. So if delta G is less than equal to 3 and we want to apply BC degree 3 algorithm, then we also need the vertex of degree 2.
Okay, that's correct, right? So how did VC degree at most 3 resolve itself, right? If it had a vertex of degree at most 2, it applied the same algorithm, else it increased the parameter by little bit 1 and then applied this algorithm.
So how about assuming here that the graph has a vertex of degree at most 2 even for BC degree 4?
I cannot assume that. I will like we will come up with there will be cases where we will not be like, so when we will recursively branch on a vertex, okay, I will not be able to maintain that invariant. You understand my point?
No, because then if we are not maintaining it, Then how can I apply VC degree 3?
Because how did we apply VC degree 3 before? If this graph was a 3 regular, we subdivided this as increase the parameter by 1 and then call this algorithm.
Yeah, right.
Yeah, that's it. But it will only happen once, no? Because once you get to a degree 3 case, you will never come back to any other case that you will have to apply again and again this thing.
Right.
That's why.
Yeah. Okay.
Right? So VC degree 3, it checks, is my degree is the input G equal to 3 regular? If yes, subdivide this as do this and then I'm going to call this algorithm. Okay? And after that, once I have maintained that invariant in the beginning, I am always able to maintain this, right? So I only increase this parameter once in any branch and that's it.
Okay.
Suppose there are 3 regular components, there are many connected components and each of them are 3 regular, then we apply.
We'll get back. So first of all, this observation is wrong or right?
Connected graph.
It is only correct about connected graph. And if the graph is not connected, what should I be doing it? I should be applying my algorithm on each of this component independently. Then it is not multiplication, it is sum. You understand my point? Even if I increase my parameter here, right? It's not the multiplication, it is a sum. Okay? So this is exact. If I had a 2 different components, connected component C1, C2 ... CL, my algorithm is going to first work on this, right? Suppose it got some running time, then it is plus this running time, it's a plus this running time, it's not multiplication. So even if I increase my parameter to k plus 1 here or here, will it matter? No, right? So whenever you have a disjoint connected components, this is always sum, right? Does that make sense to you, right? So but look, so our algorithm always will work on each of these connected components separately, right? And once you are working on a connected component, okay, and you made this change by invariant property, okay, then that even when you make many components, that invariant property will hold across that component. You get my point, Sanjay? No.
Across the component where you made the change.
Yeah, so once I made this component, right, then only region it might not hold at some point of time. Why it doesn't hold? Because yeah, but but even when this happens, even if it happens several times also, because this gets distributed, it won't change. So it's not like I solve an algorithm here, right, then I multiply with the running time of this. No. No, you don't understand this?
I think I will do, but I want to write it down.
So how did you do in polytime algorithm? Think about it. I will give you an example. Then there's a bottleneck in your polynomial time understanding of algorithm. Okay, imagine that I have 2 components. Just has size n1 and size n2. In fact, they are n by 2. There is n by 2. Okay. Now let's fix your problem, any problem you wish, whose running time is like it's quadratic algorithm. So what will the running time on this component? And on this component, then this is it not? Yes or no?
It depends on problem.
Exactly. For vertex code, does it matter? Right? That, so I am not, so whenever you are taking so what is, I take a solution here, does the vertex cover if I find locally here and locally here, does it matter if, then, so I should be summing up the running time, no, I shouldn't be multiplying the running time. and that's it. So what is my algorithm? My algorithm, it works on each connected component first, solves it, keeps the solution, works on the second connected component, solves it, keeps it. So what does it returns, you think? Right? It just returns the sum of the running time of each connected component. Okay. So yeah, so this is, one has to understand this, and I'm not denying it, but it is important that you ask this question. So in general, this statement is not true. Right? Because what could have happened, I have a connected component which is 3 regular and everything else is like say 4 regular, 4 regular. So there is a graph which has a vertex of degree at most 3, there exists a vertex of degree at most 4, but there is no vertex of degree 3 which has a neighbor 4, right? Okay. Right? So, but if G is connected, okay, so now we need this extra assumption that G is connected. Okay. Now if G is connected, then why such a vertex exist? Okay. So the simple idea is very simple. Look at all the, suppose these are like V 3 vertices, okay, and these are say degree 4 vertex. Even this statement may not be true, right? Should this be true at all? Even then this is not true. Even this is not true. I can give you an example why it is not a true. This is not a true statement, because I could have a degree 3 vertices, okay, and this vertex is adjacent to some degree 4 vertex, right? This is my graph, this is connected, okay. So if I assume here, so this is exactly, so if I assume that my minimum degree also is 3, then I know that this graph either has a vertex of degree 3 or 4, okay. Now we will be good, okay, and we can reach there, that's not a big deal at all, okay. Okay, so now before we get there, we need to add something to our algorithm, right? If there exists a vertex V of degree 2, there exists a vertex V of degree 2 in G, apply, let's say, apply 2.2, right? Apply 2.2 and 2.3 of VC degree 3, right? That's it. Right? So this is my step. So now when I reach a 2.2, what stage we are in? What is this? Minimum degree is at least 3. There exists a vertex of degree 3 and there exists a vertex of degree 4, right? So now we are in this case. Now if we are ready to apply this observation, then what? Then now can I prove such a vertex? Okay. Why? Because look at all these vertices. What is the property of these vertices? This is say V equal to 3 and this is V equal to 4. And now this graph is connected. So if this graph is connected, there is a vertex here, right? And there is a vertex here because I know there exists a vertex V here and there exists some vertex Z here, right? So now because this graph is connected, there is a path from V to Z, okay? Look at the first time vertex leaves this V3 and enters this. What is the property of this vertex? It has a neighbor here, right? So that is the vertex we will pick. Okay. So connectivity implies what? There exists a vertex V with neighbors x, y, z, and what is the property of z? Degree of z is equal to 4 and degree of v is equal to 3, and that's it. Okay. So if none of these things apply, I am able to reach this. Okay.
In the observation, it is not written there that vertex V should have degree 3 actually. There exists a vertex V who has a neighbor of Z.
There exists a vertex v of degree 3 which has, yeah, that's what I wanted. Okay. And I will tell you why I want this, because now there is a very beautiful property. V has degree 3, right? So the moment I branch on Z, so the side which I do not want Z to be included in my solution, what happens on V? What is the degree of V? 2. That is exactly why I am creating this 3-4 imbalance, that the moment I delete Z in my graph, V is a vertex of degree 2. That's the only reason I have done all this hard work. Okay. Now you can do many more case analysis here, but I will only do up until this and leave it. Okay. So now I will tell you what will this algorithm lead to. Okay. So I do not want to change this. You understood what this proof is, so let's go. Okay. Now notice what happens. Here is a vertex V which has a 3 neighbor x, y, and z. I am not even like, if I start looking into this neighborhood, there are many beautiful properties that one can exploit, but I do not want to do that. All I care about is that Z has 4 neighbors, 1, 2, 3, maybe, I do not know how they are, and V has degree 2. Now let us branch on V. Branch on V, okay, sorry, Z. So in one side, Z goes into the solution, so parameter drops by 1. In other side, Z does not go into the solution, Z does not go into the solution, my parameter drops by 4, right, 4. So here it is 4, okay, okay. But now look at this. But now the moment I delete Z, here I want to do a bit more hard work, because just leaving this recurrence here is not, so I want to somehow call several subproblems with more parameters, drop, and then analyze my algorithm. Okay. So now when I go, I have a very beautiful situation. My situation is that V is a vertex of degree 2. Okay. Now I should fold V, that will drop by 1, but the moment I fold V, it is possible that this vertex has degree greater than or equal to 3, right. Now it is greater than or equal to 3. Now I am not sure at that point of time that I am maintaining this invariant. You understand my point, right? So to maintain this invariant, what is important, that the moment you do fold, if it is not satisfying this good property, then branch on that, right. So for example, but here I could branch much nicely, because I could, when I could just say that, look boss, now when I said greater than or equal to 3, right, I could just say if V0 has a degree greater or equal to 4, only then branch, because if it is 3, then I have nothing to do, because in this invariant I am maintaining the fact that there exists a vertex of degree 3, my witness. V0 is the witness that this graph has a vertex of degree at most 3. Only time when I should be branching on V0 is when V0 has suddenly become 4 or more, like then I do not know whether there is any other vertex of degree 3 or not, like I just absolutely do not know. But then the moment I delete V0 or its neighbors, then I am guaranteed in the recursive solution I do have vertex of small degree, because this is the only anomaly and every other vertex has degree at most 4, right. So what is happening in the recursive algorithm is that at any point of time, if we create a problem vertex, we immediately branch on that problem vertex and make sure that this does not exist in my recursive branches. You get my point? Okay. So let's look at this. So now we are in this case. Okay. So what is the step? Okay. V has a neighbor Z of degree 4. Okay. Now what I am saying, okay, branch on G, fold branch on G by including fold V if V0 has degree greater equal to 4, no more 3, greater equal to 4, branch on V0, branch on V0, okay, and branch on n of z. Okay. So what happens now? Now here, look, lots of fun thing happened. Okay. Okay. So first of all, here one drop because of fold, right. So either I can stop here or I have to branch on this V0, but what is that branching? It's 1, 4 branching, right. So I branch here on V0, 1 here and 4 here. So now let's look at how many subproblems I create and what is the change of the measure. So I create one subproblem here. What's the change here? Is 4. Okay. How much do I change here? 1, 2 and 4. So 4, 5, 6. How much do I change here? 1, 2, 3, right. So either I do this or I could have stopped here at V0. Then in that case, my would have, like, if I would have just stopped at fold, how much my change would have been? 2, 4. Look, if I did not branch on V0, I branched on V0 because this guy became degree 4 or more and I am not sure my graph has a small degree vertex or not, right. If it already was degree 3, then I said I am not going to branch. Your algorithm will take care of it because I am maintaining the invariant that there exists a vertex of degree at most 3 in my graph. Okay. Now, so there is a branching like this and there is a branching like 3, 4, 6. What's the running time of these two? So what is this? It is this is going to be 3, 4 and 6, no? So what will this solve to? It is x power n less than equal to x n minus 3 plus x n minus 4 plus x n minus 6. So it is x power 6 should be less than equal to x power 3 x square plus 1. Is that fine? Yeah, so I am just solving my Wolfram alpha. There's nothing else I'm doing. Huh? 1.30. Are you sure? Either I did something wrong here.
U4 is like 1.1.
Okay, so x power 6 equal to x power 3. Maybe you are right. I did something wrong. X square plus 1. Please do it for yourself, just for fun. You are right. It is this. So this will solve to, this recurrence solve to 1.304 1 to the k. And how much does this solve to? 1.227. Okay, fine. That's something. Okay. So what's the running time of this algorithm now? We already made this algorithm, we are done. So what's the running time of this algorithm?
1.3.
Okay. You can do much better than this, I am not doing it. Okay. 1.3041 to the power k. Okay? Okay. So how people go? So now let me give you, so is this fine with everybody? I am not going to mess my hands beyond this, but I will tell you how people mess their hands without doing computation. Is that fine with people online? Maybe I should be running.
Yes.
Okay. So if this is fine, then now let me tell you how people mess their hands more. Okay. So this observation is my starting point. Okay. So yes.
So can we do it also for the vertex of degree 5, 6 using the same?
Of course you can do. This is what people do. It's just that I stopped doing that. Okay. I already stopped doing it. Look, the best running time is roughly like this for the general vertex cover. So, and I stopped even for 4 at 1.3041. So imagine, like, I'm just telling you that I am not in mood to mess my hands. Okay. But yes, you can. Otherwise, how will you reach here? Right. So how people mess their hands? Let me show you how people mess their hands. Look at degree 3 vertex and look at x, y, z. Okay. Okay, I am not talking about z, you know, is a degree 4. Okay. Now imagine yourself that there is some optimum solution that contains y and z. Then do you need to, then what can you say? If you are anyway going to take y and z, then you better also take x and go ahead, right? So there exists an optimum solution that either takes, so what is this? There exists optimum solution that either takes x, y, z, or at most one of x, y, or z, right? So the moment you pick 2, right, I can always exist a solution which contains all the 3. Right? So there is no point. It's like once you decided to do y, z, v becomes degree 1 vertex, then you better pick x. It's like that, right? So this is a crucial observation. Okay, now if this is a crucial observation, then imagine yourself first. X, y, z has a triangle on them. Then what can you say? Imagine that x, y, z formed a triangle. You bet, because you know that any minimum solution will pick both, at least 2 of them. The moment you pick at least 2 of them, you better pick all 3 of them and make it a reduction rule. So you take all the 3, reduce. This is like a reduction rule. So you can assume now that the graph does not form a triangle. Fine. Okay. Okay. So you start doing all these kind of things. Okay. I'm not very good at it, but like I need to sit down and okay. So now I'll say, okay, fine. Okay, suppose there is a vertex here who has at least 2 neighbors here. Okay. Okay. Or okay, so there's at least 2 neighbors here. Then I can say, oh, if there's at least 2 neighbors here, then I can do some other branching. Oh, then I know this forms an independent set. Okay. If there's even one edge you have, then you know at least you have to pick x and y. Right. So what is the kind of solution? So imagine that I had an edge xy. I add an edge xy in this graph, then you know that at least one of them vertex you need to pick, right? So the moment you pick one guy, you will start getting this degree 2 and many more things. So you start exploiting those facts, right? Otherwise you say, okay, fine, there are no edges here. Now let's look at and then look at their common neighbor. If this is also a common neighbor of 2 vertices, then I can do something. So they do not have a common neighbor. If they do not have common neighbors, then how many neighborhood of this is there? Okay, you do yourself. Okay, all I'm saying that you start with this observation and you start to mess with it and start doing it. Okay, that's it. Okay, so that's all. But it's good for people to go and mess their hands once. Okay. I am not doing it because it's not very, let's say, it's not very representative for the class, but for an individual, it's a very representative to go and try their hands out. Okay, but now my whole objective was to make an algorithm for general graph. So what should be I do? VC general. What should I do? C equal to phi while C is equal to less than K and J is not empty. Okay, J is not empty. What should I do? Now I will say 2.1, if there exists a vertex V of degree greater than equal to 5, branch on V. Okay, 2.2, if maximum degree of G is at most 4, call VC degree 4, and I am done. That's it, right? So what is the running time of this algorithm? There is bounded by this, but there is also another branching vector which is, but degree 5 now. So this is like T of K is less than equal to T of K minus 1 plus T of K minus 5. Okay, so what is this? Wow, excellent. So this is like 1.32 to the power K. So this is faster than your algorithm.
So I wrote 1.36 for K because I wanted the exponent on the number of these to be K.
Sir, this algorithm is better than your algorithm. That's all that I'm saying. Okay. Okay. Look, I looked at what you sent me. It said 1.36 or something, which is fine. I'm not necessarily fun. Okay. So what did we see in a class? In a class, we saw an algorithm for vertex cover that runs in time 1.32 something to the power K. And the best known algorithm is like roughly 1.272 to the power K. Okay. Now, right, 1.27 to the power K. This is roughly, this is for the general graph. Okay. So going from here to here is a long way forward, because the reason why I did not try to optimize here for two reasons is that even if I get better algorithm here, right, where is my difficulty? My difficulty is this. This is my difficulty. This is not my difficulty, right? So why should I try to make my hands dirty if this is what my bottleneck of my algorithm is, this branching algorithm, not this. Like even without doing anything, I got 1.304. So if at all I want to go below 1.3 for vertex cover in general graph, I have to do something with this, which I was not willing to do. You understand the point, right? Without changing this or without rectifying this branching vector, there is absolutely no way we can reach 1.30 and below. But it's a good question. Can you at least beat this algorithm by doing something interesting? Okay, but here is something which is a question for you people, is analyze this algorithm. Here's an exercise, okay, and please take my exercises seriously. Okay, so what is an exercise? Analyze this algorithm in terms of n number of vertices. I promise to you, you should get better than 1.3, because if when you say number of vertices, the side when I include its neighbors, I become isolated vertex. So my recurrence is not k minus 5, it will be n minus 1, n minus 6. Okay, so every recurrence, at least some places, will increase by 1, and that should give you a better running time. Okay, so there, if you want to go much better, so there people know how to do better than 1.2 itself, 1.19 something. For, I told you, right, so roughly for general graph it is like roughly 1.27 to the power K. So for general graph, as far as I remember, it is this, something like this for general graph. Okay, like if you follow this, and this has stood the time for last 12 years. Okay, so that's all that I wanted to tell you about vertex cover, recursion, branching. Okay, so now I want to, so if I remember the chart I draw, I said, okay, at this point of time, either we try to improve the algorithm that we have got for vertex cover, or take a completely different regime of work. And what is a different regime of work? Could be that try to find parameters or way to measure the running time of this or try to come up with an algorithm for vertex cover with parameter which is smaller than the solution size. Okay, so now let's try to understand what kind of questions we could come up with, what kind of parameters we could come up with, and how do we go about designing those algorithms. Okay, so is all fine up until now? Because we will completely change our gears now. Okay. You want to take picture? You can. Yeah, but not mine. Didi, you can take, it's fine. It's okay, then I will rub it. Otherwise, look, it has everything which I taught today on the board. Okay, so now I can rub, right? Okay. Okay, so let's go back and write down our vertex cover problem. Input is G, comma K, and the question was, does Z has a vertex covered of size at most K. Okay, so up until now we have seen algorithms with two parameters. One, we said find n number of vertices, and then we started with 2 power n algorithm, and if you do some maths here, you should get something below 1.3 to the power n by whatever we did today. Okay, and then we said fine, but n sounds too much, like it doesn't seem to be more interesting or whatever. So then we started to use K size of solution. Okay, and here what did we saw today? After lots of hard work, roughly this algorithm. Okay, now I want to, so in my regime of parameters, okay, here is K less than equal to n. I want something here. Can you give me some set of parameters which is smaller than K? Like I want to know, like, I mean, this vertex cover so good that any parameter I'm choosing, it turns out to be FPT, or can I move? So if that is the case, can I come up with a more and more smaller, like provably a smaller parameter with respect to which I can show that it is FPT, or I can show that maybe we shouldn't expect such algorithms. Okay, so let's try to see. Let me give you one such example. So here is my S solution size, and what was this graph? What was G minus S? Independent set. This was an independent set, right? Now, it was a very useful thing, right? So, what is an important thing? That there was something very important feature that you never bothered in our algorithm. What was the important feature? Base case. What was our base case in all our algorithm? Is graph empty or not? Up until now, this is what we have used, but we also have used some other base cases. Okay. So what was the base case? What was our base case? First base case was, is G empty? And what I mean by base case? I mean by base case where we stopped doing recursiveness. We solved the problem like without making any more branches. What was the other thing we did? Huh? Maximum degree is at most 2. You are right, but we also know how to do an algorithm on trees or forest. Okay, so we'll get there. Excellent. Okay, so when we said, oh, look at delta G is less than or equal to 2, okay, then the problem is poly time. Excellent. That's a great base case. So now I can ask myself that, look, here you are anyway using something in poly time, okay, then why should I give you something to waste on this, right? So maybe the parameters should be something which, like, what is the utility of parameter? I am allowing my parameter to be exponential function, right? So why allow something to be an exponential, like that part of the parameter to be exponential, which we can do probably in poly time. So if I wanted to capture this notion, what kind of parameter should I come up with? So somehow what I mean by this, that the moment you reach this case, the parameter becomes 0. What kind of parameter that we can come up with such that the moment I have a graph of degree at most 2, it's 0. Yeah, no, for vertex curve we are talking about. Yeah, so what kind of parameter that I can come up with such that the moment I say, look, if this is the parameter, then on graphs of degree at most 2, this parameter is 0. Look, what is a parameter on a graph of degree at most 0? Is 0. I want a parameter such that the moment, look at this family of graphs. What is a family? G, maximum degree of G is at most 2. I want a parameter such that the moment I come here, so I want a function. Okay. So what is I want a function h from all graphs to say natural number, okay, union 0. And what is the property of this function? That the property of this function should be that if delta of G is at most 2, then h of G is 0. I want something of this. And look at in the language of vertex cover, right? So suppose beta, right? What is beta? G, I can say minimum vertex cover of G. This is the parameter, right? Now on edgeless graph, what is beta of G? Is 0, right? So if G is edgeless, beta of G is equal to 0. So basically what vertex cover problem we try to do is trying to compute, is the beta of G at most k? That's exactly what we try to do, right? Is beta of G at most k? This is the question. But forget about this, just as a parameter. Now I want to come up with a different parameter. And what is the property of this parameter? That this happens. So can you think of a parameter like that? Coloring. Like any, you can come up with any trivial parameter. Why? Number of vertex is not like, come with if the graph of like, if minimum degree is at least, if the delta g is not 2, it's the number of vertices, and if it is delta g, it's 0. This is also very well interesting parameter. No? Look, if all that I required you is this, right? So you define a function, any function that on these graphs is 0 and on anything else it's 1. Whether it is interesting or not interesting is a very different question, right? But I could come up with a function here. What this function does? Check. If delta of g is more than 2, then h of g is 1, okay? Else h of g is 0. I never demanded anything, right? All I asked that, can you come up with some function? Yeah. Okay. Imagine if this is my parameter, and now I go back and I ask, now you have to solve a vertex cover problem with the following, okay? You still want to solve a vertex cover problem, but the running time of this algorithm, okay? So what is want to solve vertex cover, but the running time of this algorithm is as follows. What is the running time of this algorithm? It should be some function of h of g times n to the power big of 1. Can you come up with an algorithm for vertex cover where the running time of the algorithm can be written like this with respect to this function? Is it possible? Is it possible? Vertex cover is an NP complete problem. So can I come up with an algorithm where f of hg, like where the running time of this algorithm, I can write it down as function of hg times poly in n. If that is the case, because what is the hg? Hg is just like either 1 or 0. So this is nothing. So the problem is solved in poly time, right? So there is absolutely no way I can use this function or this measure or to analyze my running time, or it's an interesting measure, but it's like it just doesn't work out well for our algorithm. Like, so we can computationally answer this question that this is not a good parameter. Why? Because we are able to trivially answer questions like this, right? So maybe we need a different, which is more useful, right? So, right, and what was our goal? Our goal was to come up with something which is less than equal to 2. Okay. Okay. So here is one such. Let's see another function. Okay. So this is how you define this function. So what did I define beta of g? Like, so I defined for vertex cover, right? Beta of g was minimum vertex cover of g, right? This was the computer. This was the function which I associated with it. Now the moment it implied, what was the beta of g? If g is edgeless, this was 0. And now I define what is my beta of g? My beta of g is minimum number of vertices required to be deleted, say s, such that delta of g minus s is less than equal to 2. So I am asking what is the minimum number of vertex that I need to delete such that the graph has maximum degree at most 2. So this is my parameter. Now what is beta of g when maximum degree is at most 2? Is 0, right? So it scales up. But now is it obvious? But another thing, look, whatever this parameter is, okay, notice this is always less than equal to k. Why? Because what is vertex cover does? Every vertex cover is such a solution because it goes to a graph of degree at most 0, right? And this tells me that you are not allowed to go to, it says degree at most 2. So every vertex cover is a solution to this, but not every solution to this is a solution to vertex cover, right? So if you think, what is a vertex cover? I want to delete so that I reach to a graph of degree 0. And what is this parameter tells? I want to reach to a graph where degree is at most 2, right. So this should be a smaller number than the vertex cover itself. But now what is our goal? What are you writing, Satya? You look confused, right? So what is my goal now? I want to come up with an algorithm. Now let me see if any of you can come up with this an algorithm. So every base case I could come up with in my algorithm, I could get there by doing some of these kind, right? So every potential graph family that I reach as my base case, I can say, hey, I am only allowing you to do this much, okay? Okay. Okay. So this is clear. So what is our goal? There are beautiful questions that arise at this point of time. So input is this, okay? So goal will be to come up with algorithm for this, does this, but the running time of this algorithm should be, what's the running time of this algorithm? Should be f of beta of g times n to the power big O of 1. That's a fun thing. But now there are a couple of things that we need to know, right? Suppose if this is my parameter, is such a set S given to me as a part of the parameter, part of my input, or it is not given to me as a part of the input? Because if it is given to me as a part of the input, maybe I know how to exploit it. If you don't give me, maybe I have to compute it. That's a very different question. But now there are two questions, right? Question number 1. Is S such that delta of G minus S less than or equal to 2 given as input? Question number 2. Such S is not given as part of the input. Okay. Right. And these two parameters could be very different from each other, in the sense that there are family of graphs, right? There could be a family of graphs where you need to delete only some constant number of vertices to get a graph of degree at most 2, but if you look at the vertex cover, it could be very much. Right? For example, look at K, like disjoint union of K4s, for example, right? But this is not a good example. Yeah, this is also a good example, no? You take K4s, okay? Make this point center and this. How many vertex do you need to delete here so that the graph has degree at most 2? Center vertex. But what is the vertex cover of this graph? Count for yourself. It's huge. So this parameter could arbitrarily be different from each other. You understand my point? Right? So there are families of, look, we always know that this parameter is lesser equal to vertex cover. That's okay. But in fact, there are families of graphs where one could be much larger than the other, right? Example, these families of graphs. So then we ask some of these questions also. So they are like becomes a combinatorial questions, how these parameters behave with each other, relate to each other. But now there are a couple of questions, right? 1 and 2. So this is one set of questions we'll try to address. So I'm not trying to answer anything anymore, okay? I'm just trying to ask questions. So this is one set of things that people can ask and people can do. Okay. Now let's try to understand some vertex cover centric questions. Okay. Someone told about forest. He was talking, oh, we can also solve forest in polytime. Yes, right? So then what can be the parameter for forest? Okay, because we know how to solve vertex cover in polytime on forest. So we could ask, what's my parameter? F from family, so let's call this parameter theta from G to natural numbers union 0. So what we want this Okay, if you give me a forest, it should be 0. So first let's set that out. If G is forest, then theta of G is 0. Okay, and if it is not forest, then what should I say? Just following the last trick, I should say, okay, if G is not forest, theta of G is minimum number of vertices required to remove such that resulting graph is a forest, right? So this actually has a name in the world. This is called feedback vertex set. Someone has an exercise, right? So this could be another parameter too, and again the same set of questions could be asked. What other graph class that you know where vertex cover is polytime? We use this also in one of our subroutines, bipartite graph. So let's put that also, no? But there is some relation happening now. What is forest? Is it bipartite? So if let's call this parameter theta FVS. Okay, let's call a new parameter. Let's call theta FVS, theta FVS. I'm going to call theta OCT is defined. Okay, excellent. Okay, now theta OCT of G is equal to 0 when? If G is bipartite. Okay, bipartite. Okay, and else what is theta OCT of G? I will tell you why I am calling it OCT in a minute. Okay, again, minimum number of vertices required to remove such that G minus S is bipartite. Okay, so now because what is a set of, so if the graph is bipartite, if and only if it does not have, so this is called odd cycle transversal. This also has a name in the literature. Okay, so this is called odd cycle transversal. Okay, but now notice the beta. Okay, beta and this has no relation. It may not have any relation. A graph could be degree at most 2, like, so I do not know how to compare these things, but notice that fine. This parameter is less than this parameter is less than this parameter, right? And so just to, let's call it, give it a bit different name. Okay, so I'm going to call this modulator, let's call every modulator, I'm going to call it theta delta G 2 modulator or set of vertices, which, okay. So now we have this here, theta at most 2 modulator something. Okay, now we are getting such chart of parameters, and now we don't know whether our problem is solvable with this or this or this, and again both questions, did you give me this or did you not give me this? If you give me, maybe I can solve it, but if you do not give me, I don't know how to solve it. Okay, so we will get, so ask these questions to yourself, but there are more things to do. Okay, suppose graph G has a perfect matching. G has a perfect matching. Okay, the vertex cover problem is NP hard even if the graph has vertex, like vertex has perfect matching. What is the minimum size of vertex cover here? So what is what? So I mean, if someone gave you a parameter k, say if k is strictly less than n by 2, what is your answer? No. Right? So k is greater than or equal to n by 2, only then you are in the good regime of. But then this is like a trivial algorithm, no? Like in sense, like if you are trying to understand in terms of parameterized algorithm, it makes absolutely no sense to me. In the sense, I mean, it's trivially FPT. I mean, this question whether the problem is fixed parameter tractable or not is like very obvious answer. So this is not fun. Oh, what could be the fun question then? The fun question could be that look, this you anyway need. This you anyway need. At least n by 2 you anyway need. I ask you a question, does your vertex cover needs n by 2 plus L? Okay, and you need to come, and what is this? So I am saying, do you have a vertex cover of G is at most n by 2 plus L, and now you are only allowed to use running time f of L to the power n of u. This is not allowed anymore, right? It's not even obvious that you can. So if this problem is poly time, then you can suppose this problem is FPT or anything, then you should at least be able to decide whether a graph G has a vertex cover of size n by 2 plus 35 in poly time. Is it obvious? I give you a graph which is a perfect matching, that's all that I said, and I said, hey, does it have a vertex cover of size n by 2 plus 35? Do you think it's an easy answer for this? Do you even see an algorithm which will give you, does it have a vertex cover of size n by 2 itself? Do you understand my question? Right? I give you a graph G and a perfect matching. I want to say, ask you, is the vertex cover equal to the perfect matching size, or you require more? That's all that my decision version, right? Is it? If this is FPT, what do I? At least this question we are able to decide in poly time, right? So these kind of questions also start to make sense. But then you can ask, why perfect matching? Look at any graph. Maximum matching forms a lower bound on the side of the minimum vertex cover. So people just change this question and they ask the following question. Okay, so what is this? So let's give it a name. Okay, okay, so this is, I'm going to call it above guarantee, but again vertex covered. Okay, okay. What is input? G, K. Question remains the same. Does G has a vertex cover of size at most K? But what is my parameter? Parameter is fun. Is, oh, you're not allowed to use too much of K. You're only allowed to use K minus maximum matching of G. This is your parameter, right? So the moment I say n by 2 plus L, there is a perfect matching of n by 2, right? So I only allowed you how much more you are taking. So yes, you have to find me a vertex cover of size K, but your parameter is K minus maximum matching of G. Okay. So if I look at this, right? If I look at this, I don't know how these are related, but definitely K minus maximum matching of some G is a lesser parameter, right? So we don't know whether it is FPT here, we don't know any of these questions, right? Okay. So do you at least see the iota of questions, right? Okay. Yes, every minimum, look at maximum matching, you have to pick at least one vertex from each edge, right? So you every minimum vertex cover must pick at least as many vertices as the size of the maximum matching is. So all I am trying to tell you that look, you ask this set of questions and look, in this case, in this question, these two questions are equivalent. Why? Because I can compute maximum matching in poly time. So take your maximum matching, take your perfect matching, but in other cases it is not the case. So these two questions make sense, right? But here, even if you did not give me maximum matching as a part of my input, I can compute this and utilize that structure or something for my algorithm design. Does this make sense to all of you people? Okay. And then we can start asking question. Do we have good polynomial time pre-processing with respect to these parameter or not, right? And then we reach into a different world altogether. Okay. Okay. So I mean, I just put down, and there's one more question which people suddenly started to think. Okay. So let me. What should I? Okay. So let me come here. So since we are only talking about questions, not answers, let me put down one more question, and then we'll close the class. Imagine that k vertices, I gave you k vertices and say, can you cover all the edges? The answer is no. What should I try? Okay, fine. If I give you k, at least cover maximum number of edges which is possible to cover by k vertices, right? So this is called maximum k. Okay, lots of people call it, say, maximum k, maximum vertex. Oh, okay, let's call it, I'm going to call it maximum coverage VC. Okay, so what is an input? Input is G, K and number T. I'll give you a number T. Okay, I say question, does G has k vertices that cover at least T edges? Okay, because I wanted to write the decision question. So I'm saying, if I give you k vertices, can you find me k vertices that covers at least T edges, right? And what is my parameter? K. If T equal to M number of edges, what is this question? It's the same classical vertex cover. Okay. Now because I'm not demanding that you cover all the edges, okay, all the edges, this question is also called partial vertex cover. Okay, is that fine? Okay, so now we have so many questions, we hardly have any answers. Okay, so what we are going to try to do from next week onwards, pick up one of these fronts and try to answer some of these questions at least. Okay, so that's the plan for the next month, to answer these questions. Okay, the fun thing will be whatever vertex cover tricks that we have done, try on this problem and see how you fail. Everything that you have learned should fail there. Okay, I have given you answer that everything that you have learned up until now will fail on this question. Try branching, try this, try that, it will fail. It should fail. Okay.